Hello there, Mr. Sutton here, bringing you this BC Calculus 8-3 Extra Practice number 2 solutions on vectors. For this one, we just want to find the velocity and acceleration vector given this position vector. So for velocity, we just have to take the derivative of each of these components individually. So we've got, let's see, using our power rule, 6t, comma, 6t squared. And now that we have the velocity vector, we just need to take the derivative of that to get the acceleration vector. So going one component at a time, we can say that a of t is going to be 6, comma, 12t. For this one, we're trying to figure out the velocity and acceleration vectors given the position vector here. So we just need to take the derivative of each component to get the velocity vector. So let's do the x component first. That's going to require the product rule, so let me set up the box and ribbon. I've got a t and an e to the negative t, whose derivatives are 1 and negative e to the negative t. Multiplying that out with the ribbon, I've got, let's see, e to the negative t minus t e to the negative t. So that whole thing is my x component of my velocity vector, my x prime. For the y component, I just have a negative e to the negative t, so that one's not so bad. Now to get the acceleration vector, I need to take the derivative of my velocity components. So for the x piece of this, I'm going to have negative e to the negative t. And then this whole thing is going to be a product rule. Now we've already basically done that product rule over here. When we did the derivative of positive t e to the negative t, we got this whole component right here for velocity. So the derivative of the negative version of that is just going to be this stuff right here, but with opposite signs. So we're going to have negative e to the negative t plus t e to the negative t. And then for our y component, this is going to now go back to positive e to the negative t using our chain rule with that negative 1 inner derivative. And if you wanted to, you could simplify this. This is negative 2e to the negative t plus te to the negative t. And that's about as good as it gets. For this one, we want the velocity and acceleration vector for this position vector. So for velocity, we take the derivative of each component individually. So we've got 2t plus, using the chain rule here, 2 cosine of 2t, comma, 2t. And then this is going to be another chain rule, and it's switches the sign when you take the derivative of cosine. So this will be positive 2 sine of 2t. And now for the acceleration vector, we pretty much do the same thing over again, but with velocity. So take the derivative of everything here. So we're going to have a 2 plus another chain rule here. So this is going to actually be minus 4 sine of 2t, comma 2, and then we'll have plus 4 cosine of 2t. To find the velocity vector, firstly, on this one, given the position vector, I just need to take the derivative of the x and y components independently. So using the chain rule, for this first piece here, I've got negative 3 sine of 3t, comma, this will be 2 cosine of 2t. And then for acceleration, we need to take another derivative. So that's going to be negative 9 cosine of 3t, comma, this will be negative 4 sine of 2t, and there it is. For this free response problem, we have a particle moving in a plane so that its position at any time greater than or equal to 0 is given by this x and y function here as a function of time. For our first task, we're trying to find the velocity vector and speed of the particle at time 5 pi over 4. So to get the velocity vector at that time, we just have to find x prime and y prime of 5 pi over 4. Now, because I'm just taking the derivative of functions that I already know at a specific value, I don't actually have to show what those functions, what the derivatives look like algebraically. I can just take the derivative on my calculator and give back the number. So let me go ahead and do that. So as a first step, I'm actually going to enter my x and y parametric functions in the calculator as y1 and y2. And then quitting out of there, I'm just going to take the derivative of those at 5 pi over 4. So let's see here. Let me do math 8. And I'll do dx. And I'm going to do x first here. So let me do alpha trace y1. So I'm plugging the x function in there. That's what y1 was at time 5 pi over 4. So let's see here. We can just do 5 times pi divided by 4. The PEMDAS will work out just fine. And then that's going to equal about 2.828. So that's the x value of the velocity vector at that time. And now for the y value, let's go ahead and do that. So I can actually just yank my input from before, but instead of doing y1 derivative, I'm going to do y2 because I want the derivative of y now. So let me do alpha trace y2. And I've got the same t value that I'm plugging in there. So press enter, comes out to exactly 0. So there's our velocity vector. Now to find the speed, I have to take the square root of x prime of this squared plus y prime of this squared, like so. Now the good news is I already know the values of x prime and y prime of 5 pi over 4. X prime was this number right here. 0 was the value of y prime. So I can actually do this without a calculator. If I take this value and I square it and I add 0 squared to it, I basically get 2.828 squared. If I turn around then and take the square root of that, I just end up with 2.828. So no calculator. Boom. All right. Our next task, we want to know if the particle is moving to the left or right at this time. Well, for that I have to look at the derivative of x. I notice that my x prime value, 2.828, is positive. Therefore, that means I am moving to the right at that time. For this one, the components of the velocity of a particle moving in a plane are given down below here. And the position of the particle at time 0 is 2, 6. We want to find the position of our particle at time 3 and also the distance it travels from time 0 to time 3. All right, let's start with the position first. So for that, we're just going to use our fundamental theorem. And we're going to do it one component at a time. So to get the x value at time 3, I have to start with my initial x value of 2, and I have to add to that the integral of the change in x, the rate of change of x, so dx over dt, on the time interval from 0 to 3. So integral from 0 to 3 of dx over dt, and we'll have a dt there. So you could call it x prime of t if you want, same thing though. So let's do that on the calculator. Since I'm going to probably be using these functions multiple times, and just to make it more manageable, I'm actually going to put my dx over dt in my y1 of my calculator, and dy over dt, while I'm in there, I'm going to put that in y2. So we're doing 2 plus the integral from 0 to 3 of x prime. So we've got 2 plus, and then math 9, integral 0 to 3. And I wanted to do x prime, so I stored that in y1, so alpha trace y1, and then put an x in for dx, press enter, comes out to exactly 20. Hey, what are the chances? Now to find the y value at 3, I need to take my initial y value of 6 that was at time 0, and I have to add the integral from 0 to 3 of y prime of t dt. Going back to the calculator for that, I can actually yank my input from before and just change a couple things. So I'm going to change this initial value here to 6 instead of 2. Still the same interval for the integral, and for the function, now I need y prime instead of x prime. So I'm going to go to alpha trace, and I'm going to put y2 in there, because that's where I stored y prime, and then press enter to get 9. So my position then is 20, 9. Now to get the distance traveled, I am going to need an integral for that. I basically have to take the integral of the speed of this function on the interval from 0 to 3. So integral from 0 to 3 of square root of, and then the sum of the squares of the derivatives in there. So I just have to do this on the calculator, since dx over dt and dy over dt, or x prime and y prime, are already defined up here for me. So here we go again. So here's what this looks like on my calculator. I've got my integral from 0 to 3. We have a square root. And again, dx over dt, that's really y1. y2 is the other one. So pressing enter on this, we get, takes a little while here, 19.343. They didn't give units, so we don't give units. We just give the number. For this, we want to find the position of a particle at time 3 and the distance it travels from time 0 to 3, given the components of the velocity of the particle down here. And we also have that the position at time 0 was 3, negative 2. So to get this started, let's find the x and y new coordinates individually. For the x coordinate, I'm going to need to take my initial x value of 3, and using my fundamental theorem, I'm just going to add to that the integral from 0 to 3 of this dx over dt, which you could call x prime if you wanted to. Either way, it's this function here from 0 to 3. So let's do that on the calculator. To make things a little bit cleaner on the calculator, and just in case I need to reuse these, I've entered dx over dt and dy over dt into y1 and y2 respectively. So now I can just pull them back whenever I need them without rewriting them. So quitting out of there, I need the integral from 0 to 3 of y1, and then I'm going to be adding 3 to that. So let's do 3 plus math 9 to get integral, 0 to 3. And again, I need y1 because that's where I stored dx over dt. So alpha trace y1. And then dx, press enter. That's about 4.386. So that's the x value of the particle at time 3. Now for the y value, we need to take the y value at time 0, which was negative 2. And pretty much just like we did over here, we need to add an integral from 0 to 3, the initial time to the new time, of y prime of t dt. Going back to the calculator, we can do this a little bit faster now that we have the stuff for x in there. I'm just going to arrow up and get my input from before, and I'm going to change it a little bit. So this 3 needs to be a negative 2. I'm going to insert a negative in there, and then let me just make that into a 2. I can use the same integral, except I have to change this y1 to a y2. So alpha trace and pick y2, because that's where I stored my y prime of t. And then press enter, negative 1.7. So 4.386 comma negative 1.7, that's our new position at time 3. We also wanted the distance the particle traveled from time 0 to 3 though. So for that, I'm going to need the integral from 0 to 3 of the square root of x prime squared plus y prime squared dt. So basically the integral of the speed from time 0 to 3. Let me go ahead and do that on the calculator. Now to do this on the calculator, since we've already got x prime and y prime entered as y1 and y2, we can do this pretty quickly. So just math 9 again, 0 to 3 integral. And this time I have the square root of, and now I have to square both of those. So alpha trace y1 squared plus alpha trace y2, and square that. And we'll put a dx there, just so it matches the variable we've been using all along on the calculator. Press enter, and that comes out to 1.419. On this problem, I have a point moving in a plane so that we have the x and y values given at different times. We have this parametric setup here. For my first task on this, I want to know the speed of the point at time 2. So for this, I'm going to need to know the derivative of the position, so the velocity basically, the x and y of the velocity at time 2. And I'm going to need to square those and square root that whole thing after I add those together. While I don't technically need to know what the derivative looks like algebraically in order to do all that on the calculator, I am going to need the algebraic version of the velocity for part B here when I find the acceleration vector. So I'm going to go ahead and find the derivatives of x and y algebraically first. So x prime, I can write that as, let's see here, this would be negative 5 sine of pi t over 6 times a tail of pi over 6. So that would actually be 5 pi over 6, negative 5 pi over 6 sine of pi t over 6. There we go. And then for y prime, this is going to be, let's see here, we have a tail of pi over 6 that we're going to get. So that's going to be a 3 pi over 6, so pi over 2 cosine pi t over 6. So there's x prime, there's y prime. To get the speed, I need x prime of 2 squared plus y prime of 2 squared, all of that square rooted, like so. And this I'm just going to do on the calculator. To make my task a little bit easier, I've entered x prime and y prime in my calculator as y1 and y2. So now I just have to take the square root of x prime of 2 squared plus y prime of 2 squared. So I've got a square root. And now to do x prime of 2 squared, I'm going to do alpha trace to pull up x prime, which was my y1 function. I'm going to plug 2 into that, and then I'm just going to stick a square out there. Next, for y prime, we're going to do pretty much the same thing, except this time I need alpha trace y2, and we'll plug 2 into that as well. Square that, and just press enter. 2.399. Okay, in calculator we trust. Moving on now, we need the acceleration vector at time 2. So for this one, acceleration is the derivative of velocity. So I'm going to need x double prime of 2 and y double prime of 2 in order to find acceleration at those times. Now the good news is that because I already know what x prime and y prime look like algebraically, I'm allowed to take the derivative of those at a specific t value without actually showing you what x double prime and y double prime look like algebraically. So I don't have to find them like I found x prime and y prime of t here. I can just move on to the next step on the calculator. So let me show you that. So first, we'll take x double prime of 2. So let me do math 8 to get my derivative. We've got dx, and I'm going to do alpha trace y1. So I'm taking the derivative of x prime. That's going to give me x double prime. And I'm doing that at a value of time 2, input of 2. That gives me negative 0.685. Now I'm going to do the same thing for y double prime of 2. So on my calculator, I'm actually just going to yank my input from before. And instead of taking the derivative of y1, now I'm going to do alpha trace and get the derivative of y2. So that's y double prime I'm finding. Press enter, and that's negative 0.712. So there's our acceleration vector. For this problem, we have the position of a particle in the xy plane given by x equals t squared plus 1 and y equals ln of 2t plus 3. And this is valid for all times greater than or equal to 0. We just want the acceleration vector for the particle in terms of t. Well, let's get the velocity piece of this first. So I need the first derivative of these. So for x prime, we've got 2t. And for y prime, we've got 1 over 2t plus 3 times a tail of 2. And I'm just going to simplify this, or rewrite it actually, because I know I'm taking another derivative. So I'm going to rewrite this y prime as 2 times 2t plus 3 to the negative 1. All right, let me go ahead now for the acceleration and take another derivative of each of these components. So derivative of 2t, x double prime, is going to give us just 2. And for this next one, let's see here, we've got negative 2 times 2t plus 3 to the negative 2 times a tail of 2. We have a chain rule going on there. And then simplifying this second one here, this is going to be, let's see, negative 4 over 2t plus 3. And the only reason I bothered simplifying it was because I have to match an answer choice. And now that I've done that, I can match this with the answer choice E. On this free response problem, we have an object moving along a curve in the xy plane with an x and a y component as a function of time. And we're told that the rate of change of x, dx over dt, is this function right here. And dy over dt, they did not explicitly give that to us. We're also told at time 2, our object was at position 3, 5. So based off all that, our first task is to find the x-coordinate of the position of the object at time 4. Well, we know the position at time 2. We know the x value of the position. It's 3. So to find the position at time 4, x of 4, I need to take my initial time, or initial position of 3 for x, and I need to add to that the integral from 2 to 4 of this dx over dt function, or x prime of t, you could call it, either way. So let me go ahead and do that on the calculator, since this is a calculator problem. Before I do anything else on here, though, I'm actually going to put my dx over dt function, 2 plus sine of t squared, in my y1 of the y equals. And I'm going to use an x instead of a t, but my calculator is okay with that. And now that I've got that in there, because I feel like I'm going to use it multiple times, let me do 3 plus, and now we need an integral, so math 9. And then we're going from 2 to 4 with this integral. I need x prime in there. Well, I stored that in y1, so alpha trace y1. And then I'll do a dx. It says dt here, but I'm using x's for everything. That'll make them function the same way as the t's do in this problem. So pressing enter on that, we come up with 6.942. On this part of the problem, we're told at time 2, derivative of y with respect to t is negative 6. Based off this, they want an equation for the line tangent to the curve at the point x of 2, y of 2. So basically, the position at time 2. So if I'm doing a tangent line equation, I need an x, a y, and a slope. I've got the x and the y. They said at time 2, the object's position was 3, 5. So really all I need is the slope. But to find the slope, I need the slope of y with respect to x. So in order to get dy over dx with these parametric equations, I really need to do y prime of t over x prime of t. Or in this case, y prime of 2 over x prime of 2. We know what y prime of 2 is. They already told us. It's negative 6. So now we just have to divide negative 6 by whatever x prime of 2 is. Since I've already got x prime defined up here, this dx over dt function, I can actually just do that on my calculator and write this part of the answer. It's not the whole answer, but it's at least a step in the right direction. So here we go on the calculator. So to do this on the calculator, I'm going to get my fancy fraction. So alpha y equals n over d, and then I'll do a negative 6 up there. And downstairs to do x prime of 2, well, I stored x prime as my y1, so I'm going to do alpha trace y1. And then I'm just going to do parentheses 2. That plugs 2 into x prime. And that equals negative 4.826. Okay, so now I just need to write the equation of my tangent line. So using point slope form, we're going to have y minus the y value 5 equals my slope that I just found of negative 4.826 times x minus the x value 3. On this part of the problem, we want to find the speed of the object at time 2. So it's crucial to recall for this one from part B that y prime of 2 was negative 6 because they didn't give us that. They didn't give us an explicit function for y prime, so we have to use this one little value here. So now to get the speed, I just need the square root of x prime of 2 squared plus y prime of 2 squared. And I can find x prime of 2 again on my calculator, so let me just plug all that in now. So here's what I've got on my calculator. X prime I stored as my y1, so I've got y1 of 2, and I'm squaring that. That's x prime squared of 2. And then y prime of 2 squared is just negative 6 squared. So pressing enter, we end up with 6.127. For this last part of the problem, for time greater than or equal to 3, we're told the line tangent to the curve at any point has a slope of 2t minus 1. All right, that might be useful later on. They want us to find the acceleration vector at time 4. So to do this, we essentially need to do x double prime of 4, comma, y double prime of 4. X double prime of 4 is not going to be a problem. We already know x prime of t in general up here, this dx over dt function. So I can just take the derivative of this function at time 4 on my calculator. I don't even need to show what the derivative of this thing looks like. And then I'll have x double prime of 4. Y double prime of 4 is going to be a little bit more of an issue because they didn't give me dy over dt. I don't know even what y of t looks like. So this is a bit of a problem. So that's where this other piece here about the line tangent having slope of 2t minus 1, that's where this is going to come in handy. So just to write out what they're saying here, they're saying dy over dx equals, because that's the slope of the tangent line, equals this 2t minus 1. Well, dy over dx is really the same as y prime of t over x prime of t. So they're saying that y prime of t over x prime of t equals 2t minus 1. And the reason that's important is because if I wanted to, I could define y prime of t by just multiplying both sides by x prime of t. I could write y prime of t equals x prime of t times this 2t minus 1 stuff. And now I actually have a definition of y prime of t. It's defined in terms of x prime, which we already have a function for. So now that I've defined y prime, I could just take the derivative of this thing at 4, and that would give me y double prime of 4. So now let me go ahead and do x double prime of 4 and y double prime of 4. And the rest of this is going to happen on the calculator. All right, so here we go. To do x double prime of 4, I'm going to do math 8, so that gives me my derivative, dx, and I need x prime in here, so let me do alpha trace y1, that's where I stored x prime, and just put 4 in there for the box for x equals, press enter, and that's a value of negative 7.661. All right, 1 down, 1 to go. This next one is a little bit trickier. So I'm going to take the derivative of this expression here, but I've got to be careful when I do it. So I'm going to do math 8 again, dx, and since this is x prime times 2t minus 1, I'm going to put in x prime, so alpha trace y1. But now you can't just write parentheses 2t minus 1, because the way your calculator thinks, if you just write a parentheses next to this, it's going to think you're trying to plug 2t minus 1 into x prime. But we don't want to do that. We actually want to multiply 2t minus 1 by x prime. So one way you could do this is to actually put a multiplication symbol. I know we don't use that very often, but you could do that, and then you can put parentheses, and we have to do this in terms of x now, so 2x minus 1. Close that parentheses. And now we should be good to go if we just put a 4 in there. That comes out to negative 50.204.